Okay, class, this is on chapter 5. I'm going to go through this one really quick. Z-scores, or the normal distribution, what it tells you about raw scores. The standard normal curve is used with Z-scores or Z-scores to determine relative frequency. We kind of went over that with the homework. Characteristics of sampling distributions, means, standard error of the mean, how sampling distributions of means are used with Z-scores to determine the relative frequency. So the relative frequency, this is about the same thing as a frequency distribution. It is a frequency distribution. We're just standardizing this and putting it on a normal distribution. This is a normal distribution, and this is called the Z distribution. We have a positive side here, and we have a negative side here. The mean splits the distribution in half, and that will only occur in a normal distribution. If we have a skewed distribution, then our mean is going to follow the skewness, or the extreme scores that are going to skew the distribution to the negative side or the positive side will determine which way that mean is going to follow the skewness. So if you have a skewed distribution to the negative side or a negatively skewed distribution, your mean will be over to the left. It will be negatively skewed. That means that the mean will not split the distribution in halves. The median would do that. Like any Z-score, location to is to the distribution. So a Z-score can be anywhere on that distribution, and we've made it pretty easy with Z-scores. We've put the mean at zero with a standard deviation of 1. So we'll have positive numbers and we'll have negative numbers. A Z-score describes a raw score's location in terms of how far above or below the mean it is. And it is measured in standard deviations, like I said. The formula for a Z-score or a Z-score is the raw score minus the mean divided by the standard deviation of the sample. And if we don't have the standard deviation of a sample, we can use the standard deviation of the population to estimate that, that standard deviation. When a Z-score and the associated standard deviation of the sample and the mean of the sample are known, this information can be used to calculate the original raw score. The formula is the score, raw score, is equal to the Z-score times standard deviation plus the mean. Using the Z distribution to interpret scores. The Z distribution is a distribution produced by transforming all raw scores in the data into Z-scores. Here, like I say, is the mean. In this particular situation or example, we have Z-scores here, and like I say, the Z-score has a mean of 0. Always will have a mean of 0 and a standard deviation of 1. If it's on the positive side of the distribution, we're going to have positive 1 would be 1 standard deviation above the mean, 2 would be 2 standard deviations above the mean, and 3 would be 3 standard deviations above the mean. And we're going to go to the negative side, and we're just going to have negative scores just like this. So in this particular example here, we've got Sean, Chuck, and Brandon, and we can take their raw score of 35 and we can place it onto this normal distribution. As long as the distribution is normal, we can find out exactly where they fall on this distribution. Well, if they're in the normal range, like Sean is, he's still in the normal range, kind of halfway in between the mean and the first standard deviation. And we've got Brandon over here who excelled on this particular exam, it looks like. And we've got poor old Chuck here who didn't do so well. So we can find out where they fall relative to everyone else on a particular test. Like people have to take the ACT test, the SAT test. That will determine how well someone's going to do in college. Well, if you're going to go into grad school, the GREs test, like the graduate records exam, that's going to be a test that will determine how well you will do in graduate school. And it's based on this same principle. Well, we know that if you score average or above the mean, you're probably going to do okay in grad school. But if you fall over here and this side below average, the chances are that you're not going to do so well, or you're going to struggle. So we can do a lot with z-scores. As long as the distribution is normal, we can determine what a z-score is based on a particular raw score. A z-distribution has the same shape as a raw score distribution. So as long as it's normal, it's going to be symmetrical. And that what symmetrical means, it means it's going to be the same on the positive side as it is on the negative side. The mean of any z-distribution is always going to be 0. The standard deviation is always going to be 1. But it's going to be either positive or negative. So if I have a positive 1 standard deviation above the mean, that just means 1 standard deviation above the mean. So if I have 2, it would be 1 plus 1, so it would be 2 standard deviations. And if it's on the negative side, it would be a minus 1, or if you add another one, it would be a minus 2, and so forth. Remember, on the normal curve, plus and minus 1 standard deviation will make up 68% of the distribution. So most all scores are going to fall between plus and minus 1 standard deviation, because that's the largest area of frequency that occurs. And while I'm on that, plus and minus 2 standard deviations from the mean will include 95% of the distribution, and plus and minus 3 standard deviations from the mean will include 99.7% of all the area in that particular distribution, as long as it's normal. Using the z-distribution to compare different variables. All right, so we got variables. So we've got English and statistics, 2 different variables we're talking about. So we can compare students on 2 different variables, as long as they're normal, like I say. As long as my mean is at 0. We still have those same standard deviations of 1, but now we've got raw scores in here too that we can look at. So we've got statistics. So we got Millie. Well, she scored 2 standard deviations below the mean in statistics, and it looks like she did a little bit better in English. She only scored 1 standard deviation below, but she's still below. Where Aletha here in English scored, slightly above, and that's what this is a z-score of 0.5. So it would be in between 1 and 0. So it would be right in the middle of 0.5. So she's slightly above the mean or the average, but she's still kind of in that normal range. But her score in statistics is quite well, and it would actually be over here between plus 1 and plus 2 standard deviations. So when we break that down, like I said, 68% right here, we've got 50 here, and we've got 38% between 0 and 1. So she's way over here. So in statistics, we know that Aletha is excelling. So there's only like maybe 1% of all the other students in statistics who are doing better than Aletha, because it would be over here. So basically like 99% or 98%, something like that to approximate, would be doing, worse than Aletha in statistics. So that's how we use these statistics and the percentages and things like that to determine how well someone does in comparison to their peer group. Using the z-distribution to compute relative frequency. And we've done that already, but not on the normal distribution. Relative frequency, and we've done that, can be computed using the proportion of the total area under the normal curve. So we're going to look at that whole area. And like I said, the whole area is going to make up 99.999, because our tails are never going to come to an end. They go on forever. But we can make up, we know of 99.7 percent of the distribution we can account for. And that would be plus and minus 3 standard deviations from the mean. So you count 3 positive and 3 negative, that will make up 99.7% of all the area of a normal distribution. It doesn't matter what variable we're talking about. It could be GRE, it could be SAT, it could be ACT, it could be English, like an achievement test in English or math. We always will put that, it's called a standardization. We're going to standardize that area on a normal curve so we know what those percentages are. The relative frequency of a particular z-score will then be the same on a normal z-distribution. So we can take a particular z-score and plug it in, and we know exactly where someone's going to fall in proportion to everybody else who takes that test. The standard normal curve is a perfect normal z-distribution, and it serves as a model of approximation of normalization or standardization. And it's called the normal z-distribution, or the z-score, or z-distribution, the normal bell curve. You've heard those things before. And there it is. And like I say, here's the percentages that we're looking at. The mean, mode, and median will always fall in the middle on a normal distribution. And plus and minus 1 standard deviation will make up 68.26% of the area that's underneath that particular score of plus and minus 1 standard deviation. Plus and minus 2 standard deviations. So I'm saying plus and minus 2 standard deviations from the mean will account for 95% of the area between those 2 scores. Plus and minus 3 standard deviations from the mean will account for 99.7% of the area between these 2 values. So try to remember those values. And you can see that on the beyond 3 standard deviations, we're only looking at like, that is 1/1000th or 13,000ths of a percent. So it's a very, very small number. So take that into consideration. Anything that falls within plus and minus 3 standard deviations from the mean will include almost the entire area of a particular test or variable that you're using under this normal distribution. Using z-scores to describe sample means. A frequency distribution of all possible sample means occurring when a sample is an infinite number of samples. That means there's samples and we know there's an infinite number. But we need a sample to generalize to a population. We know that there's a population out there, but there's no way that we can gather all the people in that population, so we have to take a sample. Samples of the same size n are selected from one raw score distribution, and it's called the sampling distribution of means. So we go out and take a bunch of samples, and then we take the means of all those samples. Let's say we're testing math, and we take a sample from Georgia, we take a sample from New York, we take one from Oklahoma and California, and then we take the means or the average of all those different states, and then we take the average of the average, and then that's what we call the sampling distribution of means. The central limit theorem allows us to envision the sampling distribution of means that would be created by exhaustive random sampling. So we can't do that a lot of times. But I know I can take samples of people and it will represent the population. So if I know that most men, or the average height of a man is 5'10", let's say, and that's arbitrary, I really don't know. But in order for me to find that out, I can estimate that, and then I can actually go out and test my theory. I can go out and take samples of men all over the place And as long as I'm taking a good sample, I should get a relative average of the true population. Excuse me. And if I do a good job of sampling, I'm not just going to, basketball games and getting a bunch of tall guys, but I'm going to, venues or places where most people go. And I take a good sample of men and I measure their heights and I take the average and then I find out what the average of men, the average man's height is. So that's how we do this. So what the central limit theorem is saying, if I take enough samples, then the samples will represent all the areas of the normal curve. Because if I go out and take a small sample, there's a 99.7 chance that I'm going to catch that true sample. Well, if I come back in, if I draw a sample, if it's plus or minus 2 standard deviations from the mean, well, there's a 95% chance that I'm going to catch the true sample in that area. And then if I come in closer, plus and minus 1 standard deviation, there's a 68% chance that I'm going to catch the true sample mean in that distribution. So the more sampling I do, I will find out that I'm catching the true sample mean. The standard deviation of a sample distribution of means is called the standard error of measurement, or the standard error of the mean. And basically, we just take the standard deviation of a sample, and basically we're going to estimate the population standard deviation. And basically what this is the standard error of measurement, or the standard error of the mean. And basically we're going to estimate what the population standard deviation is by the sample that we take. So this is the standard deviation, and basically this particular symbol is going to be the standard error of the mean, but this is actually the standard deviation, from your sample, and we're going to estimate that by the population, and we're going to divide that by the square root of our total number of observations that we have. That's how we get that. So all the sampling that I do, I'm going to take the square root of that and find out what that number is, and I'm going to divide it by the standard deviation of my sample. So the formula for computing a z-score for a sample mean is your sample mean minus your population mean divided by the standard error of the mean. It's not real difficult, but what we have to do is we have to assume that we have a population standard deviation, and we estimate that by our sample standard deviation. So if I have this data set here, and I want to find out what the z-score is for a raw score of 13, and then what the raw score for a z-score is of -2, I can do that. So if I have a raw score of 13, I can standardize that raw score, and if I have a standardized score, I can actually convert that back into a raw score too. Well, here's how I would do it. I would take my score minus my sample mean, and I would divide it by my standard error of measure, and like I say, that's going to be the standard deviation. So we know that, X bar, or my sample mean, is 13.67, and my standard deviation is 1.56. So I'm going to take my raw score, my raw mean here, or my score, I'm sorry, and subtract the sample mean and divide it by my standard deviation. That just means the standard deviation of my sample. And basically what I get is a negative 4.3. So if I remember, that's going to be in standard deviations. So I'm going to take that normal distribution, and I know that this is on the negative side now. I know that for sure. It's not quite a half of a standard deviation, so you would know what that is. So you'll know what this score means relative to the entire distribution. So I know it's below the mean, and I know that 50% of all the observations on the positive side of the mean account for 50%. So this is going to be, somewhere in the middle of -1 standard deviation from the mean. So 68% of the area of observations would be from the mean to -1 standard deviation. So this is kind of in the middle. So you look at 50% and about half of 34%. So you can kind of estimate what someone's score is relative to everybody else. Well, this is when I want to convert my score to a raw score. So I have a raw score that is equal to my z-score times the standard deviation plus the mean. So let's look at that. So I've got a mean of 13.67, and I've got a standard deviation of 1.56. So in order to do this, I would look at a -2, and that's a z-score, times 1.56 plus my 13.67 is going to give me a raw score of 10.55. So that's kind of how I would do that one. So if we know that our mean is 13.67, our population mean is equal to 12, and our standard deviation is equal to 2.5, what is the z-score for the sample mean? So what I'll do here is I'll take this formula and I'll just break it down into this type of formula here. So I'll look at all my population estimates, and I know that I have an N of 18 from that distribution we had just a few minutes ago. And I'm going to look at, this is going to be, remember, the standard error of measurement. So I'm going to take 2.5 and divide it by the square root of 18, which is going to give me a value of 0.589. And then I'm going to use this formula to actually figure out what that z-score is. So I'm going to take my sample mean, is 13.67, minus 12, which is the population mean, and I'm going to divide that by the standard error of measurement, which is 0.589. And when I do that, I get an actual standardized z-score of 2.84. Now, on the homework and things like this, the final test, I'm not going to make you do all this stuff. I just want you to have a good idea of where these numbers come from when we talk about the standard error of measurement. The standard error of measurement it's kind of like a standard deviation of error. I know when I've got a standard deviation of scores, well, I've got that. I know what that is. It's a standard distance from the mean. But the standard error of measurement is a standard distance of kind of like the mean of error. So if I have 5% error, well, I've got a standard distance from that particular mean of error. And that's basically what this is. So we have to plug in error into these things because nothing is perfect because we're not dealing with perfect parameters. Our distribution tails go on for infinity because they're not closed. We could have standard deviations of 20. We just don't know what those parameters are. And that's it for now. I'll be back with another video.